Hi, everyone, and welcome to another exciting edition of the Hardware Software Interface. And in this video, we're kicking off a new module of the course where we're looking at embedded systems. And so I thought it would make sense that we should, at this point, take a deep dive into basically what is an embedded system. Right, before we actually build an embedded system, before we look at the actual kind of technical specifics that it takes to really build one, we should really have a good idea of some of the history behind it, of what constitutes an embedded system and how it differentiates from other types of computing systems. To understand this, we got to dig a little bit into the history. Understanding that, and I actually find this is a very interesting topic, is just thinking about how fast computing systems have developed and evolved over the last 80 years or so. Okay. Now, as most of you know, right, if you go into the early days of computing, 40s, 50s, you're talking about entire rooms, right? You're seeing things like this. This is the Colossus. This was used as part of cracking the German code during World War II. So in the early 40s, this is often referred to as like the first digital computer. And this is a big, massive machine, right? And this is famous for, if you ever saw the movie The Imitation Game, you get a little bit of the history of Alan Turing and the folks, some of the great British computer scientists that really paved the way for the field of computing and laid a lot of the theoretical framework, and eventually cracking the German Enigma code and saving lots of lives. So the first digital computer, and what I find is kind of funny is that this is a picture that was included in Popular Mechanics in 1954, and what was predicted of what a personal computer might look like. And I mean, what I love the most on this is looking at how you have like that big, like almost like steering wheel type thing going on in your personal computer to have at your home. This contraption, also from the 50s, being lifted on a forklift, believe it or not, right, that is actually a hard drive, right? In 1956, storing a whopping 5 megabytes of data and weighed over 2,000 pounds. And you think about if you have a terabyte little flash drive in your pocket, you're talking about 200,000 times difference. So what I'm kind of getting at here is what we're heading in towards is looking at what technical developments have taken from a historical perspective that allowed us to be able to do something that can be constituted as an embedded system. So I think like to really talk about what an embedded system is, you have to have a little bit of the history of what was kind of leading up to it. All right. Now, when we go into the 70s, this is where you start seeing a significant amount of what would be considered the early microprocessors. And this is where you're taking the functionality of a CPU and you're really getting it on a single integrated circuit, right? Or a few integrated circuits. So you have these small integrated circuits that are containing this essential CPU functionality, and you're starting to have a substantial amount of miniaturization taking place. Okay. Now, you guys have, for this class, you've got a microprocessor, right, or 2 microprocessors embedded, right, in your Texas Instrument Launchpad. Okay. And we'll talk a little bit deeper in terms of what that is and what you have access to momentarily. Okay. Now, personal computers, right? This is where you start getting in the early days of personal computers in the 70s and 80s, right? And what we're seeing here is actually a picture of 1984 for $2,500. Contained 128 kilobytes of RAM, right? And had a 400 kilobyte floppy drive. So that was state of the art, inexpensive, but amazing technology from its day. So obviously we've seen an incredible amount of continued miniaturization going on over many decades, as well as basically, so you're being able to do more with less. And I think that's interesting to look at when you see everything from cell phones to laptops, right? And that type of development. And I talk about this not to give a whole historical lesson in the field of computing, which would take a lot longer than we have today. But this is important if we're going to actually talk about, well, what is an embedded system? Well, embedded systems are made possible by the fact that we're able to have cheaper microprocessors that can be very small, that we can now embed into other type of electrical devices. So embedded systems is we're taking this like a microprocessor and we're embedding it into anything from clothes, washing machines, microwave ovens, cash registers, right? The first design or first application was really for a calculator, right? And so in the in the 90s, this is where you start actually seeing embedded systems as being something that the technology has evolved to a point where we could start having technology deployed in this way. Okay, I'll go a little bit deeper momentarily what this is. Okay, so a lot of times embedded systems are considered, like we look at the top here, and this picture is showing a lot of what would be considered special purpose devices, at least from like a phone. You have a Walkman, a camera, a watch, a video camera, right? Maybe a personal organizer or pager, right? Embedded systems are typically, they have a very limited functionality. They're designed to do a particular thing quite well, and not really usually considered like a general purpose type of computing platform. Now, a lot of times, what you see is things change. So a lot of these special purpose types of devices, a lot of these special types of embedded systems that are shown on the top of the screen here, end up actually being kind of coalesce into more of a general purpose type of platform, say with your smartphone, that encompasses a lot of this functionality. Okay, an embedded system, and sometimes it can be similar. If you hear people talk about IoT, which is a big buzzword, that stands for Internet of Things. And the big difference between an embedded system and Internet of Things is the fact that an embedded system does not necessarily have to communicate with a back-end server, right? It doesn't need to communicate over the internet. So, the Internet of Things in embedded systems, there are overlap, and like you can have an embedded system that is also on the internet, and so, if it's kind of both. And so the Internet of Things is a big growth area. We're talking about billions of devices, like special devices out in the environment that are considered IoT or Internet of Things devices. It could be everything from traffic lights that are on the network, right, to home lighting switches and thermometer, like you have like your Nest system in your home, or any of these things that are all these kind of connected devices on the internet. And so, there's definitely overlap between Internet of Things and embedded systems. You can have an embedded system that is also on the internet and having some other types of functionality happening in like a back-end server somewhere. Okay. So let's summarize a little bit about what I said, because I kind of threw a whole bunch of things at you. A couple of common aspects of a embedded system. Okay. It's usually a computer system embedded in another device, right? So you're taking some computing functionality and you're embedding it in something. Could be a refrigerator, a microwave, a car, a traffic light, a projector, a lock, right? Where you're taking a computer system and you're embedding in something else. It usually performs a small number of dedicated functions, one or a few more. You think of like a Nest system in a home, right? It's mostly designed for dealing with your temperature, right? Or if you had something, right, like a lock for your home, right? It's dedicated about allowing entry, right? So you're talking about a small number of dedicated functionality. And we're really concerned with embedded systems in terms of a number of constraints. Power is a big issue, right? We might have to have this. It's very likely we're dealing with battery powered. So we don't want to be killing batteries. So we have stringent power, performance, size, time, and cost constraints, right? We want it to be small. We want it to do its job well. We want to use as least amount of power as possible. and we don't want it to cost a lot, right? It's embedded in some other device. We're trying to, you're trying to keep costs low so you can sell a lot of a product, okay? And sometimes time constraints come up, especially if it needs to do something, right? If you imagine you have an embedded system in a vehicle that's being used to help with like some sort of intelligent braking system, it needs to happen in a certain period of time, right? And it needs to be, so it's not you have sometimes some real-time or near real-time constraints that occur with embedded systems. So timing is a big issue, okay? So we've got some general purpose types of computing systems, your personal computers, your laptops, your servers, okay? Most systems that operate on electricity and do something intelligent have embedded systems, right? So it's mostly, if we kind of ignore these general purpose type of machines or computational systems, anything operating on electricity that has some sort of intelligent behavior, it's got some sort of microcontroller in there or microprocessor in there, and it's doing something to be able to, and that would be constituting a embedded system. It has a computational component embedded within it. Yeah. Okay, just to kind of summarize, we have everything from simple examples to more complex. Simple examples might be a washing machine, a motion sensing lamp or light, a microwave oven. Okay, more complex examples would be like your automobile's cruise control or a navigation system, or some people would consider a mobile phone. I think that's a little bit kind of on the edge between an embedded system and more general purpose. A pacemaker, some sort of robot, right? Maybe more complex. Key things that would be an essential aspect of an embedded system, okay? Usually having sensors and or actuators. So sensing something out in the environment, right? It's sensing some sort of information, right? If you're thinking maybe of your Nest Home system, right? It's sensing the temperature in the home, right? Or you got a motion sensing lamp, it's sensing if motion's occurring, right? So you got some sort of sensors that are then communicating with the as sending in some sort of input into the embedded system. Then you have actuators, ways of basically doing something out in the environment. It could be everything from raising the temperature in the room, like say, hey, the heat needs to go on, or turning on a light, right? Some sort of action, maybe a motor goes on, right? Any sort of action, any sort of actuation, right, that occurs out in the environment. So you typically have some sort of way of reading what's going out in the environment and then doing something, some sort of action based on that, okay? You have your microcontroller, this is the brain. Okay, this is the brain and it's really like the physical portion of the brain. It's the hardware portion, and that's allowing the functionality to basically run some software that can apply some sort of logic. Okay, and then you have your embedded software. This is the control logic, right? You're writing some embedded control software that allows you to basically control the system, right? The overwhelming majority of the time, this is written in C. Right, which I'll mention a little bit later on, why that's the most popular choice. Okay. I don't mean to beat this to death, right? But there's an awful large number of embedded systems out in the environment. Okay, so each year, right, over 10 billion microprocessors are manufactured, and of those, about 98% are part of an embedded system. Okay. So the overwhelming majority of these microprocessors are being placed inside some sort of embedded system, right? And we're seeing examples here from everything from like some sort of medical imaging to trains to some sort of like, home media system, cars, right? This changes, over time as people innovate new ideas. Cars probably the ultimate example of an embedded system, right? They're becoming kind of, I've heard the phrase laptops on wheels. You've got an awful lot of electronics embedded in vehicles nowadays, and there's tons of sensors as well as obviously actuation. The car's literally moving and steering and braking, as well as everything from locks, windows, windshield wipers. So there's a ton of intelligent software logic being used in vehicles nowadays, and we have multiple embedded systems that are in place to be able to manage that process. Okay. It's kind of the ultimate example, and they're getting more and more sophisticated as time goes on, right? We see this both in the current growth of the market. This is the European market. as well as looking at projections. There's a massive, many billions of dollar industry, and it's projected to grow quite substantially. So if we look at embedded systems in terms of programming languages, we can see that if you can look at just C and C++, those together constitute about over 80% of the market. C++, if you haven't seen that before, it's quite similar to C. It has some additional functionality. And it's not always used that additional functionality because it can be a bit slower and requires a little bit more, it needs a little bit more from the hardware, so it's not a straight up advantage to use C++. C is the most popular because it allows an awful lot of control of what the underlying hardware is doing. Same with, you see some 5% is actually doing it straight up in assembly language, which you need even less demands of the hardware. You have that maximum level of control. So, people who are writing embedded control software, writing software for embedded systems, the overwhelming majority is dealing with it in like a C or C++ environment. Okay. The reason, as I just kind of alluded to, lots of control. I've given this analogy to people before. You may have heard me say it before, but I'll say it again. I like the idea of thinking of comparing C versus other languages, where you could look at like a language like Python, and you can think of Python, it can be you can be super productive in a language like Python, and to a lesser extent Java. But they're kind of like trains that need to run on particular tracks, right? They can do a lot, they can move an awful lot of things, right? But they're limited in where they can go based on being on those tracks, right? Where C can be super frustrating sometimes to get things done and get a lot done in a short period of time, but you have a ton of control. It's almost like someone walking and moving like a certain amount of stuff with a backpack, right? You have a ton of control of what you can do, and you can optimize things in a very direct way. Okay, sometimes can be frustrating, but because when you're thinking of an embedded system, it has an enormous amount of power, cost constraints. There's real-time constraints. That level of control becomes very important. Which some applications, a lot of applications don't have that, but for embedded applications, it can be very important to have that level of control over what's going on in the system. So hence C is extremely popular. Okay. All right. I think I'm going to stop the video here rather than make it any longer, because I want to follow up as we start going a little bit deeper into this material. We're going to look at how we can apply what an embedded system is to solve a particular problem. And we'll get deeper into that in terms of understanding some skills in terms of how to design the control systems for embedded systems, as well as the circuits. So thanks for watching. I hope this gives you a good foundation of what an embedded system is. And you're going to get that hands-on experience as we move forward of building one yourself, which is the best way to learn. All right, so thank you. Talk to you soon. Stay healthy.